Okay, this is part 2, I guess, of a 3, actually, of a 3-part series. The first example, you saw 2 videos that comprise example 1. This third one, possibly a fourth, will comprise example 2. And the reason why I wanted to bring example 2 forward was that rational functions, there's an infinite number of them, and there are so many different types in that the characteristics that we've studied are the same, but which ones apply and just exactly how you're going to apply them to making graphs are going to vary. So it's good to have at least a couple of different examples. So in this one in particular, I wanted to make it just a little bit different so that we would have to draw on some other thinking. So what I have for you now is the following function. We have a cubic polynomial, 2 terms, x cubed minus 8 in our numerator, and x minus 2 multiplied by quantity x plus 3 in our denominator. So what we might want to entertain as a first step.
Excuse the interruption. With grade 11 and 12 students who would like retakes, please report to the library now. Grade 11 and 12 students who would like retakes, please report to the library now. If your retake board would you please, if you have it.
Are VAs, which we draw from the denominator. Okay, so the factors in the denominator producing zeros. So we have minus 3 and 2. What we might also want to look at are the zeros to the function, meaning that where is x cubed minus 8 equal to 0? Okay, so if we move forward and solve this equation, x cubed equals 8, if we take the cube root, which is to undo the cubing of x, we can see that x is going to be positive 2. So right away we should take a moment and pause for a really good cause, and that is to say that x equals 2 and x equals 2 here, we have an issue. So we're reporting a VA at 2, yet we have a 0 at 2. So right away, what this is going to say to us is that there is a point discontinuity in the graph. Okay, and here's why. So from this statement here with this 0, what this means is that x minus 2 is a factor of x cubed minus 8. So from our numerator, that means that x cubed minus 8 is going to be x minus 2 multiplied by some other polynomial. That all being divided by x minus 2 on x plus 3. Well, consider this. From this, we see that f at 2, right, had we calculate the whole thing, it would give us 0 times something over 0 by 2 plus 3. So we end up with the indeterminate form of 0 over 0. So because that's not defined, at this region of the graph, at x equals 2, wherever the y value is, we're going to expect to see a hole in the graph. So there's only one VA. This one does not count. We do not have a 0 in the graph because it is not defined at x equals 2. Okay, so this is very, very important that we take note of this. So let's go ahead and begin just a little bit of sketching, because we do have an idea of where some of these critical values are going to fall. So we'll get ourselves a set of axes, and we'll plot what we have. So we do have a VA, and that VA is at minus 3. So let's say that that is here. Go ahead and use a dashed line to indicate that trend. Okay, so there is our VA. I'll color code it too, make it special, at -3. Next, it was mentioned that at x equals 2, that there is a hole in the graph. But just exactly where does it happen? Like, where along here is the y value? Or where along here is that y value? So that's what we're going to set out to determine at this point in time. So the location of the hole in the graph. Let's do that. So what we'll do is we really need to figure out what this other factor is. We really do need that. And irregardless of what it is, take note that when you simplify this, these factors drop out, meaning that whatever we figure out for the numerator divided by x plus 3, when we substitute in the value of 2 into the equation, we're going to end up with the location of the hole in the graph. So in order to find that missing factor, if x minus 2 is a factor of x cubed plus 8, that very well means for us that long division is necessary. So let's try some long division. So we'll take x minus 2 as our divisor, and then x cubed minus 8. So in between we'll have to introduce a quadratic and linear term, and we'll begin the process of long division. So the next term will be positive 2x subtracting negative 4 from 0 gives us positive 4. Bringing down the minus 8 means that the final term will be positive 4. So here we have 4x minus 8 with a 0 remainder. That's good news. So where we see the question mark from above is where we will insert the value of, or not the value, but the expression for our quotient, which is x squared plus 2x plus 4. So let's go ahead now and we will determine the value of y where the hole in the graph occurs. So taking a new page, we'll begin that process. So f at 2 would then be 2 squared plus 2 times 2 plus 4. This is all coming from that function equation, and then the denominator would be 2 plus 5. So it looks like we'll have 3 4's in the top. It should be 2 plus 3, ladies and gents, in the bottom. So we end up with 12/5, or if you like, approximately 2.4. So back to the graph we go. Let's remove these question marks here, and we'll plot that value. So marking off some form of scale, 2.4 is roughly, say, in this region here. So at a x value of 2, we have a hole in the graph where y is equal to 2.4. So now that we have this information before us, there really is only one critical value that we need to test, and that is the VA at -3. The critical value at 2 simply means that there is a break or hole in the graph. So we're not going to concern ourselves with the behavior or the sign of the function there. So let's go ahead and set up an interval table like we did in example 1. This time we'll see if we can get the number correct. So we have 2 intervals, a column necessary for our factors. We need a heading row for the intervals, and then we'll need 3 more to complete our table. So along the top, we'll see x less than minus 3, x bigger than minus 3. Our factors will be from the simplified form because x minus 2 and both top and bottom did cancel. So they will have the same sign irregardless of whether we use them or not. So let's go ahead and figure out the signs of the quotients for each interval. So it looks like upon testing, if we were to determine, say, f at minus 4, you would see a positive and a negative and overall negative. If we tested f at minus 2, we would see positives all the way through. So we can go back to our graph and indicate what should not be used when graphing. So the regions of the graph that we can cancel out are going to be anything that is positive to the left of the VA, and then anything that happens to be negative over here. So we'll speed this up a little bit more. I'm just going to create a box and color in that box. I'll make it so much easier. Perfect. Okay. I'll leave the scale visible, but this region should not be used. So our next step is then to determine just exactly what the graph is going to look like. So I think we can appreciate the fact that the graph is going to have to somehow appear in the bottom left-hand corner, not intersecting the VA, and from what it looks like, not intersecting the x-axis. On the right-hand side, it remains to be somewhat skeptical as to what the graph is going to look like. So notice that the way that the graph is structured looks nothing like the last example. And I think that begs the question, is there anything different about the function equation that we need to be concerned with? And we should. Notice that the power in the numerator, the degree is 3, but in the denominator, the 2x's give us a squared term. So recall that when the degree of the numerator is 1 more than that of the denominator, we should see a slant asymptote.
Please excuse this interruption. This is a last call for individual photos. Anybody in grade 7 to 12 who would like retakes or was absent on first picture day, would you please report to the library now? This is the last call for individual photos. Anybody who would like retakes or was absent on the first day that photos were taken, would you please report to the library now?
So recall that the polynomial that we got from long division was this one here, x squared plus 2x plus 4. We're going to divide that by the denominator, that which remains, which is x plus 3. And this is fine, because recall that we do not need the x minus 2's, because between top and bottom they divide out anyways. So the equation of our SA will be derived from the quotient that we get from here. And if we move forward with this, I think you'll notice, I'm not going to write all the steps down, but you will get x minus 1. And if we were to complete this process, right, the long division process, just fill all that in, you'd end up with 7 as a remainder. Okay, so what that means is that therefore the quotient to x squared plus 2x plus 4 divided by x plus 3 would be equal to x minus 1 plus that little fraction of the divisor left over, which is 7 over x plus 3. So because we're talking about an asymptote, and in this case a slant asymptote, very similar to HAs, we look at the end behavior to find out where are the y values going. So as this function approaches infinity, so that is as the x values get large in either direction, what we're going to notice is that the 7 over x plus 3 is going to get infinitely small and tend towards 0. So what that implies is that x minus 1 plus 7 over x plus 3 is going to tend towards x minus 1 plus 0. So therefore, as x goes this way, we can see that the function f at x is going to tend towards a particular function itself. In fact, a straight line, or what we call a slant asymptote, x minus 1. So therefore, the SA is y equals x minus 1. So now we can go back to our graph and we can add this particular line on that has a slope of 1 but passes through a y value of minus 1. Let's just double check that. Exactly, of minus 1. So I'm going to grab the line tool and we'll use a different color here. We'll grab orange again. So passing through minus 1 with a slope of 1. So we're going to see something like this. And that's going to continue on in both directions. And there we have our SA of y equals x minus 1. So what we'll do is we'll film this in 2 parts. So we'll end this off here and we'll continue.